Welcome back to Explain the Podcast, where we take topics that leave you scratching your head and turn them into aha moments. You know those light bulb moments?
I love those.
Yeah, today we're diving into the world of binary search trees.
Ooh, sounds complicated.
It might sound intimidating, but trust me, by the end of this, you'll be seeing these trees everywhere. Now, before you run for the hills thinking this is some advanced forestry lesson, just imagine this.
Yeah.
You're in a library, right?
Okay, I can picture it.
And you need to find one specific book, but the library is absolutely massive.
Oh, yeah, that's a nightmare.
Searching randomly would take forever, right? A binary search tree is like having a super efficient Dewey Decimal System for data. It helps you find what you're looking for really, really fast.
So it's all about organization.
Exactly.
Yeah.
Now, before we get into the nitty-gritty of how these digital trees work, I'd love to hear from you. Have you ever come across the term binary search tree before?
Yeah. Let us know in the comments where you've encountered them. Maybe you've used them without even realizing it.
But that happens more often than you think.
Definitely. So let's unpack this. What exactly is a binary search tree and why should you care?
That's the big question.
Well, one of the most interesting things about binary search trees is that they belong to this special group in computer science called dictionaries. Now, to understand what makes them so special, it helps to compare them to something called containers. Imagine a container like a giant box overflowing with random books.
Like my to-be-read pile.
Exactly. You can store tons of books in there, but finding a specific one, oh boy, good luck with that. Dictionaries, on the other hand, are all about order. They use keys, kind of like those Dewey Decimal numbers in our library analogy, to make finding information a breeze.
Makes sense. So are BSTs basically just super organized dictionaries?
You could say that they're a special type of dictionary that takes this efficiency to a whole new level.
I'm intrigued. I get why searching quickly is important, but don't we already have other ways to organize data, like those sorted arrays or hash tables? What makes BST stand out from the crowd?
That's a great question. The real magic of BSTs lies in their structure. It's all about hierarchy. Picture a family tree.
Okay, I'm visualizing it.
Each piece of data is like a member of that family, a node in the tree. And each node can have a maximum of 2 children, a left child and a right child. All the keys that are smaller than the node's key branch off to the left, and all the larger ones go to the right.
Wait, so it's kind of like a choose-your-own-adventure book for data?
Yeah.
You keep making decisions left or right until you find what you're looking for.
That's a fantastic way to put it. Let's say our BST is holding the numbers from 1 to 10, and you're on the hunt for number 7.
Okay.
You'd start at the root of the tree. Let's say that's number 5.
Right.
7 is bigger than 5, so you go right. Then you might encounter 8. 7 is smaller than 8, so you go left. And boom, there's 7. You found it in just a few steps.
Okay, color me impressed. That's pretty efficient. But what happens when you add or delete data? Doesn't that mess up the whole tree structure?
That's where the real cleverness comes in. Adding and removing nodes are done in a very specific way to make sure the tree's order is always maintained. It's like having a self-organizing library that constantly rearranges itself to make things easy to find.
So it's like the books are always in the right place no matter what.
Exactly. Now, of course, there's a little more to it than that. The height of the tree, which is basically the number of levels, can also affect how well it performs. Ideally, we want a nice balanced BST where the branches are evenly distributed.
Balanced BST, got it.
Yeah.
But how do we actually ensure that things stay balanced in the long run, especially as the tree grows and changes?
That's where things get really interesting. There are these special techniques called self-balancing trees. They're like the invisible gardeners of the data world, constantly pruning and reshaping the tree to maintain its balance.
Self-balancing trees, huh? Sounds pretty advanced.
They are. We won't go into all the technical details right now, but trust me, knowing that these techniques exist is a game changer.
Okay, I'll take your word for it. So these self-balancing trees sound pretty high-tech, but are they really necessary in real-world situations? And speaking of the real world, where would I actually encounter these magical BSTs in my everyday life?
You'd be surprised how often you encounter BSTs without even realizing it. Think about searching a massive database. Like when you're looking for a specific product online, BSTs are often the brains behind those lightning-fast searches.
Really? I had no idea.
Yep, or those helpful autocomplete features that pop up when you're typing in a search bar. BSTs can power those too, efficiently narrowing down the possibilities with each keystroke.
So when I'm shopping online, and I use those filters to find, let's say, a pair of shoes within a certain price range, and from a specific brand, a BST could be working its magic behind the scenes.
Exactly. BSTs are incredibly versatile. They pop up in all sorts of applications.
Okay, so far, BSTs are sounding like the superheroes of data structures.
They're pretty impressive.
But I have a feeling they're not completely flawless. What are some of the limitations of BSTs? And when might they not be the best tool for the job?
You're right, every superhero has their kryptonite. BSTs are really good for working with ordered data, and especially when you need to find values within a specific range. We call those range searches. But they do have some weaknesses. Like if speed is your top priority and you don't care about the order of the data, then hash tables might be a better choice.
So it's all about picking the right tool for the job.
Exactly. Like sometimes you need a hammer, sometimes you need a screwdriver. It depends on what you're trying to do.
Makes sense. And to make things even more interesting, you mentioned those self-balancing trees earlier. They sound pretty complex. Might they not be necessary for smaller data sets where things aren't as complicated?
That's a good point. It's all about finding the right balance between efficiency and complexity. You don't want to over-engineer things if you don't need to.
So it's like finding the sweet spot.
Right. We've talked about searching and adding data and even how important it is to keep the tree balanced. But I'm curious about the actual process of adding and removing nodes, while still keeping that choose-your-own-adventure flow intact. How does that work in practice? It's all about maintaining order. Let's stick with our choose-your-own-adventure analogy. When we add a new page to the book, we need to make sure it fits in the right spot so the story makes sense.
Right, it needs to flow.
Exactly. So when we add a new node to a BST, we start at the root and compare the new key with the existing keys. If it's smaller, we go left. If it's larger, we go right.
Yeah.
We keep doing that until we find an empty spot where the new node can be inserted without messing up the order. Removing a node follows a similar principle, but it can get a little trickier if the node we're removing has children.
So it's kind of like a delicate dance, making sure every step maintains that inherent order in the tree.
You got it. It's a beautiful dance.
It is, but I'm also thinking about those scenarios you mentioned where a BST might not be the best option. Can you give us a concrete example of when a different data structure would be a better fit?
Sure. Let's say you're building a simple phone book app. You need to be able to quickly find someone's phone number based on their name.
Okay.
In that case, a hash table might be a more efficient choice than a BST because hash tables are designed for lightning-fast lookups without worrying too much about order.
So if speed is king and the order of the data doesn't matter, hash tables are the way to go.
Right. They use this clever technique called a hash function to directly map a key to its value.
Sounds efficient. I like it.
Here.
And speaking of different approaches to data structures, you briefly mentioned something called threaded trees earlier. Can you shed some light on what those are and how they differ from regular BSTs?
Threaded trees are a neat variation of BSTs. They take advantage of unused pointers within the tree structure to optimize certain operations. It's all about making things faster.
Oh, okay, I'm listening.
So in a regular BST, each node has pointers to its left and right children.
Right. But in a threaded tree, if a node doesn't have a left or right child, those pointers are used to point to the node's in-order predecessor or in-order successor instead.
Hold on. In order predecessor and successor. What are those?
Imagine you're reading a book and you want to jump to the next page or the previous page.
Okay, I do that all the time.
In a regular BST, you might have to backtrack up the tree to find those neighboring nodes.
Yeah.
But with threaded trees, those pointers are like shortcuts. They let you move directly to the next or previous node in the in-order sequence.
So it's like having bookmarks within the tree itself, making navigation much smoother.
Exactly. Threaded trees can really speed up operations like finding the minimum or maximum value in the tree, or even just traversing the tree in order.
Interesting. So they're kind of like BSTs with a turbo boost?
You could say that. They're a great example of how we can take a basic concept like a BST and tweak it to make it even more powerful for specific situations. I like it. So we've talked about searching, adding, deleting, and even some ways to optimize BSTs. But I'm curious about those situations where they might not be the ideal choice. You mentioned that hash table could be a better option for a simple phone book app. What other scenarios would favor a different approach?
That's a great question. What other examples can you guys think of? Let us know in the comments.
Yeah, we'd love to hear your thoughts.
This is a real collaborative learning experience.
Exactly. All right, before we wrap things up with BSTs, I wanted to touch on one more thing. You mentioned that some programming languages actually have built-in support for working with them. Can you elaborate on that a little?
Absolutely. Many popular languages like Java provide ready-made classes for working with BSTs. In Java, there's a class called TreeMap, which implements a self-balancing BST called a red-black tree.
TreeMap.
This means developers don't have to write all that complex code from scratch. They can just use the TreeMap class and take advantage of all its built-in functionality.
That sounds like a huge time saver.
It is. It's like having a pre-built self-assembling bookshelf instead of having to cut the wood and hammer in the nails yourself.
Perfect analogy. So even if I add items to the BST in a way that would normally create a very unbalanced tree, these self-balancing algorithms are working behind the scenes to keep everything running smoothly. It's like having a team of invisible gardeners constantly pruning and reshaping the tree for optimal growth.
That's a great way to put it. Those algorithms are constantly working to ensure that the tree stays balanced and efficient, no matter what you throw at it.
That's reassuring. It takes away a lot of the potential headaches of working with BSTs. But even with these sophisticated algorithms, are there any gotchas or pitfalls that we should be aware of?
That's a really good question. And it leads us into a very important consideration when working with BSTs: the potential for performance degradation if the tree becomes heavily unbalanced. While self-balancing algorithms can mitigate this to a large extent, it's still crucial to understand how the order in which you add and remove items can impact the tree's structure.
So even with those invisible gardeners tending the tree, we still need to be mindful of how we're planting and removing the data.
Exactly. Imagine a scenario where you add items to a BST in strictly ascending or descending order. What do you think would happen?
Let me think. If the keys are always increasing, then each new node would always be added to the right, creating a long right-leaning chain instead of a balanced tree.
Exactly. And this scenario highlights why understanding data insertion and deletion order is crucial, especially when dealing with massive data sets. It's like planting a garden. You need to choose the right plants for the soil and climate if you want them to thrive.
So it's not just about the algorithm itself,
Yeah.
but also about how your data interacts with the data structure.
Yeah.
And this is where those self-balancing trees like AVL and red-black trees really shine.
You got it. They
Okay.
constantly work to rebalance the tree, ensuring optimal performance even with tricky data patterns. They're like those self-watering planters that keep your plants hydrated no matter what.
That's a great analogy. It really helps to visualize how these complex algorithms work.
Yeah.
Okay, we've covered a lot of ground here. We've talked about the pros and cons of BSTs, their various applications, and even some of the potential pitfalls to watch out for. What I'm taking away from all of this is that even though they might seem simple on the surface, there's a surprising amount of depth and complexity to these trees.
Absolutely. And that's what makes them so fascinating. They're a fundamental data structure that pops up everywhere in computer science, from databases to search engines to even game development.
Speaking of fascinating applications, you mentioned tree sort earlier.
Mm-hmm.
How does that tie into all of this?
Ah, yes. Tree sort is a sorting algorithm that takes advantage of the inherent order within a BST. Remember how we talked about smaller keys going left and larger keys going right?
Yep, that natural sorting mechanism.
Well, if you perform an in-order traversal of a BST, you actually end up with a sorted list of all the keys.
Hold on, in-order traversal. What's
Oh,
that?
imagine exploring our Choose Your Own Adventure book. But this time, you want to visit every page in a specific order. In-order traversal means you visit all the nodes to the left of a given node, then the node itself, and then all the nodes to the right.
Okay.
It's a systematic way to walk through the entire tree.
So it's like the BST is naturally sorting the data as you build it.
Exactly. And the beauty of it is that this sorting happens implicitly without needing a separate sorting algorithm. This makes tree sort incredibly efficient, especially if you're already using a BST for other things.
Cool. It's like having a self-organizing filing cabinet.
But before we get too carried away with all the amazing things BSTs can do, it's important to remember that they're not always the perfect tool for every job.
That's true.
Yeah.
Each data structure has its own strengths and weaknesses. It's like having a toolbox full of different tools. You wouldn't use a hammer to screw in a screw, would you?
Definitely not. And speaking of different tools, you mentioned that some programming languages have built-in support for BSTs. Can you tell us a bit more about that? Absolutely. Many languages like Java, for example, provide ready-made classes for working with BSTs. In Java, there's a class called TreeMap that implements a specific type of self-balancing BST called a red-black tree. This means you don't have to write all the complex code for creating and managing a BST from scratch. You can simply use the TreeMap class and leverage its built-in functionality.
That's a huge time saver for developers. It's like having a pre-built self-assembling bookshelf instead of having to cut the wood and hammer in the nails yourself.
Exactly. These built-in classes make it incredibly easy to incorporate BSTs into your applications. And the fact that they often implement self-balancing algorithms means you get the performance benefits without having to worry about the intricacies of keeping the tree balanced yourself.
So if I'm understanding this correctly, even if I add items to the BST in a bad order, that would normally create a very unbalanced tree, these self-balancing algorithms work behind the scenes to keep things efficient.
That's exactly right. These algorithms are like invisible gardeners constantly pruning and reshaping the tree to ensure optimal growth and performance.
That's such a great analogy. It really helps to visualize how these complex algorithms work. So we've talked about the pros of BSTs, their applications, and even how some programming languages make them easy to use. But are there any gotchas or pitfalls to be aware of when working with BSTs?
That's a great question, and it leads us into a very important consideration when working with BSTs. The potential for performance degradation if the tree becomes heavily unbalanced. While self-balancing algorithms can mitigate this to some extent, it's still crucial to understand how the order in which you add and remove items can affect the tree's structure.
So even with those invisible gardeners tending the tree, we still need to be mindful of how we're planting and removing the data.
Precisely. Imagine a scenario where you add items to a BST in strictly ascending or descending order. What would happen?
Let me think. If the keys are always increasing, then each new node would always be added to the right, creating a long right-leaning chain rather than a balanced tree.
Exactly. And this degenerate case essentially turns our beautiful, efficient BST into a simple linked list, where searching becomes a linear operation instead of the logarithmic performance we expect from a balanced BST. This highlights the importance of considering the order of data insertion and deletion, especially when dealing with large data sets.
So it's not just about the algorithm itself, but also about understanding the nuances of how your data interacts with the data structure.
Yeah.
It's like planting a garden. You need to choose the right plants for the soil and climate if you want them to thrive.
A perfect analogy once again. And this is where those advanced techniques we briefly mentioned earlier, like AVL trees and red-black trees, come into play. They address this very issue by automatically rebalancing the tree as items are added or removed.
So they're like those self-watering planters that ensure your plants get the right amount of moisture no matter what.
Exactly. They take care of the intricate balancing act, allowing you to focus on the bigger picture of your application.
That's incredibly helpful. Knowing that these tools exist takes away a lot of the complexity and potential headaches of working with BSTs.
Absolutely. And remember, even if you don't need to implement these advanced techniques yourself, understanding the concepts behind them will make you a more informed and effective programmer.
This has been an incredibly insightful deep dive into the world of binary search trees. We've learned about their structure, their efficiency, their applications, and even some of the potential pitfalls to watch out for.
And we've seen how seemingly simple concepts like trees can have such a profound impact on the way we organize and interact with information.
Before we wrap up, I want to remind everyone to follow Explained for more deep dives into fascinating topics like this one. We're constantly exploring new ideas and concepts, and we love sharing our discoveries with you.
And don't forget to leave your thoughts and questions in the comments below. We love hearing from our listeners and learning from your perspectives.
Now, for a final thought before we sign off, we've talked about how BSTs are used in databases, autocomplete features, and even online shopping filters.
They're truly everywhere, working tirelessly behind the scenes to make our digital lives more efficient.
But what other creative applications of BSTs can you think of? Could they be used in gaming, perhaps, to manage complex game worlds or optimize AI decision-making?
Or maybe in music, to analyze melodies and suggest harmonies based on musical patterns.
The possibilities are endless. We encourage you to explore these ideas and see where your curiosity leads you. After all, that's what Explained is all about, sparking your imagination and empowering you to understand the world around you.
So keep exploring, keep learning, and keep asking questions. We'll see you on the next episode of Explained.
It's amazing to think about all these different ways to organize information. It's like we're building these invisible structures that make our digital world work.
I know, it's fascinating. We've talked about containers and dictionaries, but there are so many other types of data structures out there. Arrays, linked lists, stacks, queues, graphs. It's a whole world of possibilities.
So many options. It's like choosing the right tool for the job, I guess.
Exactly. Each data structure has its own strengths and weaknesses. It all depends on what you're trying to achieve.
Right? It's not one size fits all. And that makes it even more interesting.
Definitely. There's always a new challenge, a new problem to solve. It keeps things exciting.
I can see why you're so passionate about this. It's like a puzzle figuring out the most efficient way to manage information.
It is. And the more you learn about data structures, the more you realize just how clever and elegant they are. They're the hidden foundations of our digital world.
Speaking of efficiency, you mentioned earlier that BSTs are particularly good at something called range searches. Can you remind me what those are and why BSTs excel at them?
Of course. Imagine you have a database of students and you want to find all the students whose grades fall between 80 and 90. That's a range search. You're looking for values within a specific range.
Got it.
And BSTs are great at this because of their inherent order. Remember, smaller keys go left, larger keys go right.
Right, that built-in sorting.
That structure allows us to efficiently traverse the tree and quickly find all the nodes that meet our criteria. It's like using a price filter on an online store. You can instantly see all the products within your budget.
That's a helpful way to think about it. So it's leveraging that inherent order to narrow down the search quickly.
Exactly. And this ability to perform efficient range searches makes BSTs really powerful for tasks like database queries, statistical analysis, even things like finding nearby locations on a GPS.
Wow. So they're not just about finding one specific piece of data. They can help us find patterns and insights within data sets. It's like having a super organized library where you can instantly locate all the books on a specific topic.
You got it. And this ability to work with ranges of data is one of the key advantages of BSTs compared to other data structures, like hash tables, which are generally better at single-value lookups.
Okay, so each data structure has its own strengths and weaknesses. We need to choose wisely.
Absolutely. Like a chef selecting the right ingredients for a dish.
You know, I have to admit something. My brain is starting to feel a little full from all this information overload.
Haha, I understand. We've covered a lot of ground in this deep dive. But hopefully you're leaving with a better understanding of how these amazing digital trees work.
Definitely.
Yeah.
Even if I don't remember every single detail, I feel like I have a much better grasp of how data structures work and why they're so important. It's like we've peeked behind the curtain and seen the gears turning.
That's what we were hoping for. To spark your curiosity and give you a taste of this fascinating world and encourage you to explore further on your own.
And that's what Explained is all about, making complex topics accessible and even fun. We hope you've enjoyed this deep dive into binary search trees. And as always, we'd love to hear from you. What other topics would you like us to explain in future episodes?
Yeah, let us know in the comments. We're always looking for new adventures.
So keep those brains buzzing, and we'll see you next time on Explained.